for welcoming me back again. I remember 2 years ago chatting with you about black holes, and it's always a fun subject, but I thought it might be too soon to do more on black holes, and then turned around at the last minute and contradicted myself, because at the volunteer party yesterday for this group, why everyone was asking me about the new black hole discovery. You'll recall that black holes are where some mass material shrinks down to the point that its gravity gets incredibly strong and not even light can escape, and then that stuff is crushed to the center. And we have evidence that black holes exist, not because you can see them directly by definition, but because their intense gravity thrashes around material near them, which can heat it to high temperatures and make it shine, but can also make stars orbit very rapidly. As you may know, they've found in the center of our own galaxy, confirming a 4 million solar mass black hole there. It looks like in the centers of all galaxies, all big galaxies anyway, there are these giant black holes that weigh millions or billions of solar masses. What has happened recently is that some discoveries were made, including a colleague of mine, Carl Gebhardt, and others using our telescope in West Texas, have studied some galaxies looking for the biggest black holes. And in this particular galaxy called NGC 1277, they have found a galaxy that's a black hole that's the biggest ever, which is 17 billion solar masses. And what's surprising is that this is a galaxy that is a relatively modest-sized galaxy, smaller than the Milky Way. Normally, a galaxy has a black hole that's about 1/10 of 1% of the mass of the whole galaxy. Here, it's 20% of the mass of the whole galaxy. So it stands far apart from the normal relationship, and so this is going to be a subject of study. The technique for determining this galaxy is tens of millions of light years away, is to study how the stars are orbiting around the center and whether there's evidence for a special concentration of mass in the center, apart from the spread out distribution of stars that has its own particular gravitational force field, but a concentrated mass in the center has a different kind of force field, and it makes stars orbit in a different way. That, and also just the way the stars bunch up and the profile of how the stars get more and more closely packed toward the center. There are two reinforcing lines of evidence for that. So we're going to have to stay tuned to see about this. If we can advance a little bit, this is the galaxy cluster. So we've zoomed back a great deal, and kind of in the middle as an undistinguished object is the galaxy in question. But this is a rich galaxy cluster in the constellation Perseus, meaning far, far beyond those stars that form the constellation we see in the night sky. And so you can see it's a whole bunch of galaxies together there of varying sizes. And this is kind of a segue into the subject I want to talk about. If we can go on to that next slide, and I won't take you away from the award-winning music, but another 2 minutes here. Here's a beautiful spiral galaxy called M101, a nearby spiral galaxy that's just about 10 million light years from Earth. What you see are the spiral arms where compression waves are causing the gas to form lots of stars. And you can see some of the white knots along these spiral arms, like a bright one right over here. That's a good idea.
No, hold it to your mouth.
Oh, to my mouth. I thought he was saying something clever. Those are places where a whole bunch of stars have formed. Some of them are big, massive, bright, hot stars, and their ultraviolet light makes the gas heated and ionized, and it glows with a particular spectrum. It puts out certain wavelengths of light that we call emission lines in the business that can be analyzed to tell us the chemical proportions of oxygen to hydrogen. Now you know that out of the Big Bang came hydrogen and helium and nothing else. And as that gathered into galaxies that then formed stars, their nuclear reactions in the core of those stars formed heavier elements like the oxygen and carbon and nitrogen that we're made of, and the iron that's in the Earth. So as time goes on, more stars live and die and blow up and spread that stuff around, and new stars are formed, and that's why we can be here, is that our sun is only 5 billion years old. Our galaxy was around for 5 billion years before that, so earlier stars did the legwork of producing these heavier elements that then got dispersed, gathered up into new stars, one of which was our sun. And it's an interesting subject that to analyze the proportions of those heavier elements tells us something about the life history of galaxies. And one thing we know is that toward the center of a galaxy like this, chemical abundances are richer than toward the outside, where it's tilted more toward the virgin composition from the Big Bang. One bit of work we did is to study galaxies that are in clusters, and we found that that relationship of the size and the type of the galaxy and its proportion of heavy elements depends on being in the cluster environment. And so we thought we had a nice theory of that until very recently with a graduate student I found that there is a similar relationship between the nature of galaxies and the amount of gas in them and the heavy element abundances, even for galaxies that aren't in clusters. So our tidy little theory of why this happened in clusters of galaxies is now out in the open. There's just a few more pretty pictures to remind you how much fun galaxies are, and then I'm done. This is a so-called barred spiral galaxy. This is an intense one. You can see without any words from me why it's called a barred spiral. And it is thought that our Milky Way itself is one of these guys with a fairly substantial bar. Doesn't come out as far as we are from the center of our galaxy, but about halfway out. So that's the kind of object we may be living in. I think I'll quit there and turn it over to the entertainers here.